Okay, so now we're working on our last kinematics equation. Before we do, just want to remind you that if you were to, this is our equation that relates displacement, initial velocity, acceleration, and time. And if you were to take the derivative of this function with respect to time, you'd end up with this one right here. This function has to do with the fact that when acceleration is constant, your average velocity is the same thing as your starting and finishing velocity divided by 2. Okay, and there's actually a different version of this that we're going to use. Okay, and I'll show you what that is right now. Okay, to get to that version, we'll start with what we have right now. Okay, because when we're looking at all these variables, average velocity is a variable that we don't have in these other equations, and it would be nice to not have to introduce something new and have to deal with an extra variable. And so the way that we can get around that is that we know that average velocity is the same thing as the displacement divided by the time. So we're actually going to replace it with that. And so we get that displacement over time would be equal to v plus v naught over 2. And then we can actually multiply the t over and get this equation, delta x equals v plus v naught over 2 times t. Okay, and so we'll use that as our other kinematics equation for now. Okay, before we continue, what's the condition that has to be met for any of these equations to be valid? That condition is that the acceleration is constant. So all of these equations work because something has a constant acceleration. Okay? Alright, so we're going to come up with the last equation, and it's going to come from putting this equation right here and this equation right here together. Okay? And so I'm going to start with this first one. So v equals v naught plus at. Okay, and I'm actually going to solve it for acceleration. So I'm going to solve it for t. V minus v naught, we'll subtract the v naught over, equal to a times t. If I solve it for t, I'm going to divide by a. So v minus v naught over a is equal to t. Okay, and then I'm going to take this t, I'm going to substitute it into this equation right here. Okay, so delta x equals v plus v naught over 2 all times t. We're going to replace t with this. Okay, and we get v plus v naught over 2 times v minus v naught over a. Okay, and so you might notice that we have a difference of squares here. Okay, so we end up with delta x equals, when we multiply those out, we get v squared minus v naught squared, and then 2 times a would just be 2a. So I'm going to solve all this for v. So I'm going to multiply the 2a over. So delta x times 2a equals v squared minus v naught squared. We'll add the v naught over, and we get that v squared is equal to, we added the v naught to the other side, so v naught squared plus, and then all of this, I'll reorganize that a little bit, so 2 times a times delta x. Okay, and so this is then the other kinematics equation that we're going to use. Okay, and so here we have 1, 2, 3, 4 kinematics equations. The only other one that you're going to see that I don't really ever use, but you could use if you wanted to, is a variation of this one, in which that goes, instead of initial velocity, uses the final velocity, and then you subtract here. Okay. So this is a variation of that one. I don't ever recommend using it. Really, we're going to use these three, this one, and this one. And occasionally you might find a reason to use this one or that one. Okay, so here we have a scenario now that involves a constant acceleration. So there's a Porsche, we're braking it to slow down. It looks like we saw a police car, and so we wanted to pretend like we're going the speed limit. And during the time that we're slowing down, it looks like we traveled a total distance of 80 meters. Okay, and so then in this situation, there's all sorts of information that we can find just using these tools. And so here's the kinematics equations, okay? And so this will be the first one, second one, third one, fourth one, and the fifth one as we reference them. And so whenever we're approaching a problem like this, graphs can be really helpful, and it's also really helpful to identify the information we know and the information we don't know. Okay, you'll notice looking at this table that there's 5 quantities here: displacement, initial velocity, time, acceleration, and final velocity. And each of these equations has 4 of those quantities. Okay, and so you're going to see problems like this, and they're almost like puzzles, because it's like a puzzle where you're trying to find this missing piece of information, and you have this tool that compares 4 pieces, and you want to find the one that has the 4 pieces that work for you. Okay, so the quantities, though, that we can be finding, we'll write them out, and it's good to get in the habit of writing them out when you're working on a problem. We can have displacement, we can have initial velocity, final velocity, we can have acceleration, and we can have time. Okay, and so just as we're thinking of this, these 4 quantities are vectors. Okay, time here is a scalar, which means all 5 of these have magnitude, or how much. Only these 4 have direction. Okay, and so when we are setting up these problems, pictures can be helpful, and it's important that we say which direction is which. So if this is the road, and here's the car, okay, you can tell this is a really nice car, right? It's a Porsche, it's a really nice car. So it's going this way. We're going to have a displacement of about 80 meters, and we're going to say that anything going this way is positive, okay, which means anything back that way would be negative. Okay, so looking at this scenario, before we even solve for anything missing or make any graphs or anything like that, should your acceleration be positive or negative? Alright, we'll go ahead and see. Alright, so we know the displacement is going to be 80 meters. We know that we start with an initial velocity of 27 meters per second, because that's how fast we're going at first. We know that we have a final velocity of 22 meters per second, because that's what we slowed down to. And that's all that we have. We don't know what the acceleration is, we just know it's constant, which means we can use these equations in the first place. And we don't know how much time it took. Okay, so on this same note, it probably didn't have a constant acceleration, because that would be pretty much impossible. But if it was relatively constant, then we're approximating using these equations. And so we're making a prediction here based on this mostly valid assumption that's going to allow us to use these tools to make predictions that are mostly accurate. Okay, so let's say that we wanted to find maybe the acceleration. Okay, we have these 3 pieces of information, and we're looking for this 4th one. So which of these equations relates these 4 quantities together? It's not the first one, because we don't know the time, or the second one for the same reason. If you look at the third one, we see that we have those 4 quantities related together. Okay. Alright, and so we are going to plug those values in now, and we'll solve it for A. Okay, now I'm going to pause the recording and work it out real quick. If it's helpful for you to look at the work, then you can pause and look through the work. But I don't want to spend 5 minutes here working out a problem if you don't need to see the algebra. Okay. Okay. So I plugged in the values: displacement, initial velocity, final velocity. I'm simplifying, and you'll notice that I'm including the units as I work. And so the reason I do this is because it's a good way of kind of checking yourself to make sure stuff is working out and making sense. And so here I square those and I get this weird unit of meters squared per second squared. I get the same thing over here. And then I know that I can combine these because they have those same units. And then it turns back into meters per second squared when I divide over the meters at the end. Okay, and so here I found acceleration. We can put that right here. Okay, and that opens up opportunities to find time using either of these two equations. Okay, or you could actually use this one too. This fourth one right here. Okay, my recommendation, you can use any of them. When possible, it's good to avoid using a value that you had to round. Okay, because that introduces error. So we had to round this value for acceleration, and so it might be better to use this equation right here because we haven't had to round any of those numbers yet, and so our answer might be more accurate. Okay, but at the end of the day, that's not something that matters a whole lot. So if it's not going to make a huge difference, I guess. So if you wanted to use, say, this first equation right here to find time, you could. Alright, so go ahead and actually find how much time it took to change speeds from 27 to 22 meters per second and to cover that displacement of 80 meters. You can choose whichever equation. Go ahead and tell me how much time and tell me which equation you used. Maybe the simplest equation to use would have been this one right here. Again, you could have used either. I think I recommended this one right here. Okay. If you worked this out, you would have got about 3.27 seconds. Okay. If, as you worked it out, you ended up with a negative time, it's because you made an algebra error. When you subtract this over, you get a negative value, and you divide by your negative acceleration to get a positive value for time. Alright, and that's going to cover it in this video for constant acceleration.